Question 13a. How can you justify first law of thermodynamics obeys principle of conservation of energy? So we need to justify that first law of thermodynamics obeys the law of conservation of energy. And we know first law of thermodynamics is based on the fact that energy is neither created nor destroyed in any thermodynamic system. So I'm writing, okay, first law of thermodynamics is based on the fact that energy is neither created nor destroyed in any thermodynamic system. Okay, the heat Q, okay, let's say the heat is Q given to the system can cause two changes. One, it can rise the temperature of the system and thus increase its internal energy. Delta U. Second, it causes gas to expand. That is, allowing gas to do work. So we can write in this way, okay? Heat added Q equals increase in internal energy delta U plus external, okay? External work done by system delta W. So we have this, okay? Now, (13b), okay? If the thermodynamic process starts from A, so starts from A and comes to A. So starting from A, it comes to A, okay? So it ends on A. So we have this, clear? This is to be noted. Using path 1 and 2 as shown by arrows, does the net work done 0? If not, explain. Clear? And we have thermodynamic process starting from A and ending on A. Okay, so I'm writing in this way. Given thermodynamics or dynamic process starting from A and ending, okay, on A, following path 1 and 2. Okay, path 1 and 2, and direction indicated by the arrow. So we have this. So what we find, the loop is traced, okay, in this direction. So the loop is traced in clockwise direction. The loop, okay, is traced in clockwise direction. So we have this. Therefore, total work done is positive. So let us denote total work done by the symbol WT, okay? That is, WT is positive. So we have this. This is to be noted, okay? Total work done is positive because the loop or the path is traced in clockwise direction. So we have this. And next, we use this concept, okay? So I'm writing over here. We use this concept, work done, W equals integration PdV, and the limit is Vi to Vf. So we have this. Clear? We have this. And if final volume is greater than initial volume, then work done is taken positive. So we have this. And if final volume is less than initial volume, then work done, okay? So this is for positive work done. Then work done is negative. So negative work done. So we have this. Clear? Now I'm redrawing the diagram given in the question. So we have this, okay? So let us call this point, okay, as C, and let us call this as D. Okay, so we have this. So the volume corresponding to B is this, okay, and the volume corresponding to A is this. Okay, so we have this. Now we can divide this cycle, okay, complete cycle or loop, into two sections. So I'm doing this, okay. So we have section AB, we have this, and the volume corresponding to A is this and is denoted by D in the figure, and the volume corresponding to B is this and is denoted by C, okay, in this figure. So we have this, and the area below the curve AB is represented by the shaded line, okay. So we have this. So what we find, this is initial and this is final, okay. So we have this. So we find this volume at B is greater than volume at A, clear? So it means that final volume is greater than initial volume, therefore work done, okay. We use this concept, therefore work done is taken positive. So we have this. Next, section BA, okay. So we have this section BA. So this is C, this is D, and the area under the curve BA is this, okay, represented by the red line or shaded line. So we have this. Now, this is initial and this is final, okay. So what we find this, okay. We find VA is less than VB, that is volume corresponding to A is less than volume corresponding to B. So we can understand in this way, final volume is less than initial volume. So the work done is negative. So we have this. So we are using this concept, okay. We are using this concept. Now, in order to find work done, okay, we use the concept, we use this concept. So we know work done by a gas during the cycle is determined by the area of the PV diagram bounded by the cycle. Now, for path 1, so we are moving from A to B, and we find when we move from A to B, we find expansion, okay. So we have expansion. So in this case, we have expansion, whereas in this case, we have compression. So this is to be noted, okay. Therefore, work done W1, okay, along the path 1 equals area, okay. We know work done is given by area of the PV diagram. So the area is A, 1, B, C, D, A. And we have volume corresponding to B, greater than volume corresponding to A, that is final volume, greater than initial volume. So the work done is positive. So we have this. Next, for path 2, so we have this, okay, from B to A. So in this case, we have compression. We have compression and work done W2, okay, equals area, okay. So I'm writing in this way, B to A D C B. So we have this, and what we find, final volume is less than initial volume, so the work done is negative in this case. Therefore, net work done or total work done, WT, okay, is WT equals W1 plus W2. So we have this. Therefore, we can write WT equals, we have area, okay, positive area, A1 B C D A, and W2 is negative, okay, minus area B2 A D C B. Now when we subtract, okay, this, so finally we get this, okay, total area, we get this. So I'm writing over here, we get net area or total area equals area A1, okay, B2 A, and we know total work done is positive since the loop, okay, is traced in clockwise direction. The whole loop, okay, the complete loop is traced in clockwise direction, so that the total work done is positive. So we have this, clear? So I'm writing in this way, WT equals positive area A1 B2 A. So we have this. So what we find, net area, we are finding, sorry, net work done is not 0. So we have this, okay. So we find net work done is not 0. Why? Because area of PV diagram, okay, diagram bounded by the curve is not 0. Clear? So we can see, we are asked to find, does the net work done is 0? So what we have, net work done is not 0. So if not, explain. So why net work done is not 0? Because area of PV diagram bounded by the curve is not 0. So we have this area, okay, which is not 0. Now we go for question 13C. In adiabatic process, no heat is exchanged but work is done, does it mean that adiabatic process violates first law of thermodynamics? So 13C, okay? Now, we know in adiabatic process, no heat enters, okay? Enters or leave the system. So we have this. The system is heavily insulated. So I'm writing in this way. So we have this. So we have this. Now, we can understand adiabatic process in this way, okay? For adiabatic expansion, okay? For adiabatic expansion. So let us understand in this way. We have a cylinder, okay? Fitted with piston. So we have this. So we have this. So we have this. So we have a insulating cylinder fitted with piston, which is also insulating, okay? So we have this. We have a heavily insulated system. Now what we find, when pressure, okay, pressure on the piston is reduced, okay? So when pressure is reduced, so when pressure on system is reduced, okay, the gas, let's say we have a gas, okay, the gas pushes, okay, the gas pushes the piston upward due to expansion. So we have this, okay? So we have gas, okay? So it pushes the piston upward. So we need to understand this, okay? We have this. Due to this, the temperature falls. Okay, we have this. Now we need to understand why the temperature falls in adiabatic expansion, okay? So let us understand this also, okay? So we have a question generated in this part, okay? So what we find is that in order to understand this, okay, so why there is fall in temperature? The gas molecules loses speed, okay? Since we find the gas molecules, okay, they are pushing or hitting the piston so that the piston is pushed upward. Okay, so the gas molecules loses speed after colliding with moving piston. Okay, so we find the piston is moving, so the gas molecules, they're colliding with the moving piston and they are losing their speed. The loss in speed, causes fall in temperature. And from first law, okay, first law of thermodynamics, we had this. So let me write in this way. Okay, delta Q equals delta U plus delta W, and delta Q, this is 0 since no heat enters or leave the system. So this is for adiabatic process. Therefore, we can write delta U equals minus delta W. So we have this. So what we find is that when gas expand, then delta W, that is work done, is positive. Therefore, internal energy decreases, due to which, so internal energy decreases due to which the temperature falls. So what we find, internal energy is converted to work. So I'm writing internal energy is converted to work. So we have this. Clear? Next, adiabatic compression. Okay, now I'm redrawing the cylinder fitted with piston. Okay, so we have this. Clear? So we have this. So gas, and we have a heavily insulating system. Okay, now what we find in this case, okay, in previous case, pressure in the system on the piston. Okay, sorry, this is piston. This is piston. Now pressure is piston is increased. Okay, so we have this. So what do you find? Piston moves down. So we have this. Now, when the pressure is increased. Okay, so let me write in this way. Pressure on the piston is increased. It moves downward. So when it moves downward, it compresses the gas. Okay, so I'm writing in this way, compressing the gas. Now, when gas is compressed, temperature increases. Okay, so due to this, temperature increases. Okay, why? Because the gas molecules, okay, they gain speed. They come close, okay, and they gain speed. The gas molecules gain speed after colliding, okay, with incoming, okay, piston. So what do you find? The piston is moving inward. Okay, the piston is moving inward. So the gas molecules gain speed after colliding with incoming piston. So what do you find? Gain in speed of gas causes rise in temperature. Now, from first law of thermodynamics, what we have, delta Q equals delta U plus dW, and we know delta Q is 0, okay, for adiabatic process. Therefore, we can write delta U equals minus delta W. So when gas is compressed, then delta W is negative. Okay. Therefore, internal energy delta U is positive. So what do you find? It means that internal energy increases. So we find in this case, okay, internal energy is converted to work. So in both cases, okay, that is for adiabatic expansion and adiabatic compression, internal energy is converted into work. So we can tell that in adiabatic process that it supports or do not violate the first law of thermodynamics.